Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. Imagine this. You're standing in your quarters, brushing your teeth, gazing out at a breathtaking view of Earth, a swirling blue marble hanging silently in the void. You finish, walk to the galley, and pour yourself a cup of coffee. It doesn't float away. You sit, you eat, you move as you would on Earth. Your muscles feel normal, your bones strong. But this is not Earth. It's 280 miles above the planet on the world's first rotating space station, generating its own artificial gravity. Sounds like the stuff of science fiction, right? But by the year 2030, that science fiction might become fact. Humanity is on the cusp of a new era, one where long-term survival in space demands more than just rockets, satellites, and solar panels. It demands that we confront the single greatest challenge to human life off Earth, gravity, or rather the lack of it. For decades, we've pushed against the boundaries of space exploration. From Yuri Gagarin's first orbit in 1961, to the Apollo moon landings, to the construction of the International Space Station, each milestone has revealed new triumphs and new threats. One of the greatest of those threats is invisible, insidious, and ever-present in orbit: microgravity. Weightlessness might seem fun in video clips, astronauts floating, flipping, drifting like dancers in a silent ballet. But the human body is a machine finely tuned by Earth's gravity. Remove that force, and the machine begins to break down. Within days of entering microgravity, fluid in the body shifts upward, creating puffiness in the face and pressure in the skull. After a few weeks, muscles, especially those in the legs and back, begin to atrophy. Astronauts on the ISS lose up to 1% of bone mass per month. That's 12% over a year. To compare, a healthy postmenopausal woman with osteoporosis might lose 3% annually, and it gets worse. The heart grows weaker because it no longer has to fight gravity to circulate blood. The vestibular system in the inner ear, responsible for balance, becomes confused. Even the eyeballs change shape, leading to vision problems. Astronauts returning from 6-month missions often need months of rehabilitation to walk, run, or even stand without assistance. Now consider this. A mission to Mars will take 3 years, over twice as long as the average ISS stay, without a solution to the health effects of microgravity. Such a mission could be physically devastating to astronauts. Artificial gravity may be our only path forward. So, what is artificial gravity? At its core, it's a simulation. You can't create true gravity without mass. Earth's gravity comes from its enormous mass-warping spacetime, but you can mimic the effect of gravity using centrifugal force. If you've ever spun a bucket of water in a circle and noticed the water stays inside, you've witnessed artificial gravity in action. The same principle applies to a rotating space habitat. Spin it fast enough, and the occupants will be pressed against the inner walls, just like they are on Earth's surface. The physics behind this idea is surprisingly straightforward. The centrifugal acceleration, your gravity, depends on the station's radius and how fast it spins. The equation is A equals omega squared times r, where omega is the angular velocity and r is the radius. But designing a station where people can comfortably live with that force is anything but simple. Take the Coriolis effect. In a rotating space station, any motion that isn't along the rotation plane feels strange. Turn your head quickly, and the fluid in your inner ear moves differently than you're used to. Reach out to grab something, and it may not be where you expect. This can lead to nausea, dizziness, and disorientation. NASA and other agencies have studied this effect extensively. Most people can adapt over time, but the initial adjustment can be intense. To reduce these issues, you need a large radius and a slow rotation rate. For instance, a station with a radius of 200 meters spinning at about 2 revolutions per minute can generate close to 1 g Earth-like gravity while keeping Coriolis forces tolerable. But building a station that large in orbit, that's an engineering dream we've yet to realize. Still, the idea is not new. Wernher von Braun, the father of NASA's Saturn V rocket, proposed a rotating wheel-shaped station back in the 1950s. It would house dozens of people and serve as a launch point for deep space missions. The concept even inspired the iconic wheel in 2001, a space odyssey, spinning majestically against the stars. For decades, the concept remained science fiction. Until now, private companies and national space agencies are finally beginning to revisit the idea. Orbital Assembly Corporation has proposed the Voyager station, a ring-shaped space habitat that would rotate to generate artificial gravity. Their early plans involve modular construction, robotic assembly in orbit, and a scaled-down prototype by 2027. If successful, a full-scale version could be operational by the early 2030s. Meanwhile, Vast Space, another rising player in the commercial space industry, has announced its Haven 1 project, a compact space station aimed at serving as a stepping stone toward larger, rotating habitats. These ventures are still in early stages, but they reflect a growing consensus. To live, work, and travel in space long-term, artificial gravity is essential. Governments are paying attention. 2. NASA has conducted rotating bed studies, where volunteers lie at a 6-degree tilt for weeks to simulate microgravity, then spend time in a human-sized centrifuge. These experiments explore how short bursts of artificial gravity might restore muscle and bone mass. Could a 1-hour spin per day be enough? We don't yet know, but studies are ongoing. Even more ambitious are ideas like variable gravity zones, stations where different parts rotate at different speeds. One section might provide full gravity for exercise, another might offer partial gravity for lab experiments. This would allow astronauts to gradually adapt to lower or higher gravity conditions, preparing for Moon, Mars, or deep space missions. Of course, spinning the entire station isn't the only option. Some researchers propose using short-radius centrifuges within non-rotating habitats. These would be like human hamster wheels. Astronauts enter the centrifuge, spin for 30 minutes, and exit. This approach is easier to build, but poses new questions. How often must it be used? For how long? Can short bursts of gravity replace continuous force? Right now, we're at a crossroads. Artificial gravity is no longer a distant dream. It's a developing field grounded in real science, real engineering, and very real urgency. With commercial spaceflight exploding and long-term missions on the horizon, we can no longer ignore the elephant in the capsule. We are Earth-evolved creatures. Take away our gravity, and we begin to break. That's why building the first artificial gravity station by 2030 isn't just an audacious goal, it's a survival strategy. And here's where you come in. Every great journey starts with a few brave explorers, and every idea needs a community to lift it off the ground. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy exploring the frontiers of science and asking bold questions about humanity's future, hit subscribe. It's free and it helps us grow this cosmic community together. Let's walk hand in hand, or rather float hand in hand, into a future where space isn't just a destination, but a place we can call home. Picture this. You're a mission architect in the early 2030s, sitting in a control room overlooking Earth, through a wide reinforced window at the edge of a construction module. Outside, suspended in the vacuum, pieces of a vast circular frame are slowly coming together. Robotic arms work like clockwork. Welders spark. Modules drift into place. It looks majestic, peaceful. But beneath this slow ballet of progress lies an engineering monster, because creating artificial gravity in space is not just a mechanical challenge. It's a battle against physics, materials, and the delicate limits of the human body. Let's start with the basics. To create artificial gravity using rotation, we need a station that spins, fast enough to mimic Earth's gravity, but not so fast that it causes dizziness, nausea, or long-term neurological issues. But there's a problem. To make gravity feel natural, you need either a large radius or a high spin rate. Unfortunately, increasing spin rate beyond a certain threshold makes human movement disorienting, thanks to the infamous Coriolis effect, so that leaves us with one solution. Make the station big. But big in space isn't the same as big on Earth. On Earth, we build skyscrapers and bridges with steel, concrete, and heavy equipment. We can rely on gravity to help us, and we have a constant stream of materials. In orbit, every gram counts. Every bolt, beam, and cable has to be launched on a rocket, or assembled using materials mined and processed in space, an area still in its infancy, to simulate 1 g of gravity, the same gravitational force we i.e. feel on Earth. You'd need a station with a radius of at least 200 meters rotating at about 2 revolutions per minute. That's a 400-meter wide wheel, almost the length of 4 football fields. To put that into perspective, the International Space Station is about 109 meters long from end to end. A full artificial gravity ring would be almost 4 times as wide. We're talking about the largest structure ever built in space, by far. How do we even begin? Engineers today are considering a modular design approach, building the station piece by piece in orbit, either using components launched from Earth or possibly fabricated in space using advanced 3D printing. This process is inspired by how the ISS was assembled, but on a far grander and more precise scale. Every module must be designed not only to connect securely to the rotating ring, but also to handle extreme stress. Rotating structures experience immense centrifugal forces that constantly pull them outward, placing intense strain on joints, frames, and connectors. Let's break that down. When the station spins, everything inside is pushed outward. The outer wall of the ring becomes your floor, while the inner hub is your ceiling. The tension in the structural members must be strong enough to resist being torn apart. Even a slight imbalance, say one module being heavier than another, can cause wobbling or dangerous shifts in rotation. The entire system must remain perfectly balanced, like a cosmic figure skater holding a perfect spin. That means ultra-precise mass distribution, constant monitoring, and possibly autonomous systems that shift mass or adjust thrusters to maintain balance. And then there's the question of propulsion and orientation. Once spinning, the station's angular momentum keeps it stable, but what happens if it needs to adjust its orientation? Traditional thrusters could disrupt the rotation or destabilize the structure. Engineers are investigating momentum gyroscopes, magnetic torque rods, and even ion propulsion arrays to make slow, smooth corrections without compromising artificial gravity. Now let's talk about docking. A rotating station presents a unique logistical nightmare. How do spacecraft safely dock with a structure that's constantly spinning? The current leading concept is a non-rotating central hub, an axis through the center of the ring where docking, ports, and communication relays are located. Think of it like the eye of a hurricane, calm, centered, and stable. Shuttles dock there, then crew and cargo are transferred into the rotating ring via elevators or rotating arms. This system avoids the complexity of docking directly onto a moving surface, but adds new engineering layers. These connection systems must be fail-safe, vibration-dampened, and capable of precise alignment in 3-dimensional space. And remember, rotation causes structural stress not just on metal, but on humans too. Studies show that most people begin to feel disoriented if subjected to rotational speeds greater than 4 revolutions per minute. But if the station radius is too small, you'd have to spin faster to generate 1 g of gravity. For example, a station with a radius of only 50 meters would need to rotate at nearly 6.5 revolutions per minute to simulate Earth's gravity, far beyond human comfort. The solution again? Make it bigger or settle for partial gravity. Partial gravity, say Mars gravity at about 38% of Earth's, may offer a compromise. It would reduce the spin rate needed and lessen stress on the station's frame. But we still don't know if partial gravity is sufficient to prevent long-term health issues. That's one of the big unanswered questions. What is the minimum gravity humans can live with for years without permanent harm? The answer to that may come from upcoming lunar and Martian missions. NASA's Artemis program will provide the first long-duration studies of how humans cope with 1/6 gravity. The results will be critical to deciding what level of artificial gravity is required in space stations. Now, beyond engineering and biology, there's another critical factor: psychology. Life aboard a rotating station won't be like a cruise ship. The architecture must account for motion sickness, spatial disorientation, and visual illusions. Windows will be limited, because watching the world spin around you at 2 revolutions per minute can be unsettling. Designers are considering lighting that mimics Earth's day-night cycle, wall textures that provide orientation cues, and modular layouts that reduce monotony. And what about emergencies? Imagine a fire on board or a hull breach. On the ISS, you can quickly float to a safe module. On a spinning ring, emergency movement must account for centrifugal direction. Moving from the outer ring toward the center will feel like climbing uphill. Going the other way will feel like falling. Training must include artificial gravity scenarios, altered muscle response, and rapid evacuation drills adapted to rotational dynamics. Even communication is different. Sound travels normally inside the station, but movement creates new dynamics. If a section starts vibrating due to equipment failure, that vibration could propagate along the ring, creating disorienting background noise. Designers must include acoustic dampening, rotation-specific medical protocols, and customized exercise routines to maintain health. Despite all this, the allure of artificial gravity is irresistible. Imagine farming in space, plants rooted in soil, growing upright without special restraints. Imagine children born among the stars able to walk from the moment they take their first steps. That's the vision this technology could make real. But make no mistake, building the first artificial gravity station is not just about spinning metal in the sky. It's about rewriting the rules of human survival. It's about bridging the impossible gap between Earth and everything beyond. Because if we can conquer gravity itself, then the stars may truly be within reach. Picture this. You're on a spacewalk, tethered securely to the station's outer framework. The curvature of Earth rises beneath you like a giant blue-green canvas, and the stars are so close they seem to twinkle within arm's reach. As you drift, you glance over at the sprawling construction site, the rotating ring, the modular habitats, the assembly drones and robotic arms, all working in synchronized harmony. But for all its beauty and promise, this station represents humanity's biggest technical challenge to date. Building this ring-shaped world is one thing. Keeping it alive, functional and sustainable is quite another. Artificial gravity is not just a trick of physics. It's a puzzle that demands every piece of engineering ingenuity, every advancement in material science, and every human effort to make this dream a reality. Now, let's consider the 2 primary pillars of this station's design: sustainability and safety. First, we need to understand the vast amount of resources needed to bring this idea to life. A rotating space station of this size would require enormous amounts of materials, metals, plastics, energy sources, and a steady supply of water and oxygen for the crew. In the early stages, rockets launched from Earth would provide much of the infrastructure: steel beams, propulsion units, life support modules, and construction tools. But we can't rely solely on Earth-based resources forever. One option is in situ resource utilization, ISRU, mining asteroids, the Moon, or even Mars for raw materials to build the station. Imagine processing lunar regolith to extract iron, oxygen, and silicon. These elements could then be used to create construction materials like steel, glass, and aluminum, reducing the need to launch everything from Earth. This concept, still in its early phases, would revolutionize space construction by turning distant celestial bodies into giant quarries, feeding the needs of humanity's expansion into the stars. In addition to raw materials, energy is another massive concern. A rotating station requires constant power to keep the centrifugal systems running and to supply oxygen, water, and food. The most reliable source of energy for a space station is solar power, which has been the backbone of the ISS and other orbiting platforms. The station's outer ring would likely be equipped with large solar arrays to capture the sun's energy. These arrays would feed into batteries, ensuring a constant power supply, even when the station's position relative to the sun changes. But there's a twist. What happens when you rotate the station? The angle of sunlight hitting the solar panels will vary depending on the station's orientation and the speed of rotation. Designers will need to ensure that these solar arrays can track the sun, dynamically adjusting their position. It's a delicate dance of engineering. One misstep in panel alignment could result in a shortfall of energy, leaving the station vulnerable to failure. Solar power will need to be supplemented with advanced energy storage systems to avoid power outages, especially during eclipses or solar storms, which could knock out power for hours or even days. On top of this, maintaining the rotation itself is a delicate challenge. To achieve artificial gravity, the station must spin at a consistent rate. The problem, space is, well, vast, and there's no friction to slow things down. That's a good thing, as it means the station won't need constant propulsion to maintain its spin. But it also means that once the station starts spinning, there's no simple way to slow it down if something goes wrong. The only way to control this rotational velocity is through the use of reaction wheels or gyroscopes, devices that adjust the station's orientation using the principle of angular momentum. Gyroscopes work by spinning at very high speeds, and by altering their direction, they can generate the necessary torque to control the station's rotation. However, gyroscopes aren't foolproof. They require regular maintenance, and over time they can wear down or malfunction. If a failure occurs, the station could begin to spin too fast or too slowly, potentially disrupting the carefully controlled artificial gravity. Thus, an emergency system must be in place to correct the station's rotation, perhaps involving a network of redundant gyroscopes or even small thrusters that can gradually slow or speed up the spin without affecting the station's structural integrity. So far, we've only discussed the mechanical challenges, but what about the human side of things? Space is a harsh and unforgiving environment. For astronauts aboard the first artificial gravity station, the stakes are high, especially if they're going to live there for extended periods. There's a psychological component to long-term space travel that's often overlooked in discussions about technology. The isolation, the monotony, the absence of earthly comforts, these factors can affect crew morale and performance. Imagine being stuck in a confined, rotating space station for months or even years, with little physical contact from the outside world. The crew's psychological health would be just as important as their physical health. The mental strain could be severe. How do you keep people motivated when the stars outside your window never seem to change? How do you keep relationships intact in a microcosmic society where every interaction is magnified? One of the biggest challenges for mission planners is ensuring that the crew's psychological well-being is maintained. As the first artificial gravity space station takes shape, it will need to be designed with social spaces, privacy areas, and entertainment zones that provide astronauts with a sense of normalcy. But beyond that, crew members will need to have a support system, a way to stay connected with family and friends back on Earth. Telecommunications will be vital. The station will need to be equipped with high-bandwidth communication systems, capable of transmitting messages, video calls, and even virtual reality-based social spaces. This technology, already in use by the International Space Station, will become even more crucial as we extend our presence into space. However, the vast distances involved will create delays, meaning that real-time communication may not always be possible. Astronauts will need to adjust to a new type of solitude, relying on pre-recorded messages and occasional visits from crew rotations or automated vehicles. And there's another aspect of this, the crew's ability to work in artificial gravity. Many aspects of human physiology could change when exposed to consistent, Earth-like gravity. Over time, how will the body react to long-term gravitational forces, especially after years of weightlessness on prior space missions? Will astronauts experience new challenges such as heart strain or fluid retention due to a lack of adaptation? Or will the presence of artificial gravity lead to a stronger, healthier human body that's more resilient to space radiation and other dangers? Beyond the medical challenges, there's the question of how human nature will manifest in a confined, rotating world. If the station is large enough to house dozens or hundreds of people, social dynamics will play an enormous role. In its success or failure, how will the crew interact? What types of governance, leadership, and decision-making structures will emerge? Will there be divisions between Earthborn personnel and those born in space, like children who may never have set foot on Earth? The psychological implications of creating an entirely new generation of humans who have never known Earth's gravity could be profound, and yet that is a future we may soon face. Finally, there's the biggest question of all. What happens next? Building the first artificial gravity space station will be an extraordinary achievement. It will open the door to permanent human settlements on the Moon, Mars, and beyond. It will allow us to live and work in space, creating new economies, industries, and opportunities. But it will also mark the beginning of something even more profound, the next chapter in the story of human evolution. Because once we master artificial gravity, we won't just be surviving in space. We'll be thriving in it. Imagine waking up in the year 2040. You step out of bed in your space habitat, a cozy apartment inside the giant rotating space station that orbits Earth. You pull open the curtains, and the familiar blue planet is floating outside your window, now a constant companion. Below you, the curvature of Earth gives you a perspective that most people on the ground will never experience. But what's even more amazing than the view is the realization that you're living in artificial gravity. It feels like home. And what if this is only the beginning? What if, in the not-so-distant future, humanity doesn't just live in space, but thrives there? Building the first artificial gravity space station isn't just a step toward space exploration. It's a leap into an entirely new way of living and thinking about human existence. It's about creating a space where humans can not only survive, but flourish. And beyond the station, the implications stretch far into the cosmos. With artificial gravity, humanity can begin to expand beyond Earth, opening up new opportunities for colonization, resource extraction, and even interstellar travel. The potential for space-based industries is staggering. In space, there's no atmosphere to resist spacecraft, no air to create drag. That means ships can travel faster, more efficiently, and more economically. Space tourism, for example, could be transformed from a luxury experience into a mainstream activity. Imagine vacationing in space for a week or two, strolling in the comfort of artificial gravity, while gazing out at distant stars. Your trip could involve not only relaxation, but a chance to experience a truly different way of life. Zero gravity. Gyms could give astronauts a full-body workout, stimulating muscles in ways that earthbound exercise can't. Artificial gravity would make everyday life far more familiar and comfortable for civilians, reducing the health risks that come with microgravity and opening new possibilities for space-based living. But the true game-changer goes far beyond space tourism. With artificial gravity, we could build the foundations for permanent colonies on the Moon and Mars. A station in orbit around the Moon, for example, could act as a launch platform for missions to the lunar surface, providing a base of operations for resource extraction, scientific research, and agriculture. A similar approach could be taken to Mars, where artificial gravity would provide the conditions necessary for long-term habitation. We could begin cultivating crops in space, growing food in conditions that simulate Earth's gravity. Researchers are already experimenting with plant growth in microgravity, but artificial gravity would open up new possibilities for agricultural expansion beyond Earth. No longer would we be dependent on Earth's ecosystems to feed ourselves. Instead, we could cultivate our own food in space, reducing the need for constant resupply missions. This independence from Earth could become critical as we expand our reach across the solar system and even beyond. But let's pause for a moment and think about the bigger picture. The construction of the first artificial gravity space station will not only pave the way for the colonization of other planets, it will also dramatically accelerate our understanding of space as a resource. Space mining, which has often seemed like science fiction, is inching closer to reality. Once artificial gravity systems are in place, the extraction of minerals from asteroids and other celestial bodies could become a viable and profitable industry. Valuable resources like platinum, gold, and rare earth metals are scattered throughout the solar system, and having a reliable and sustainable way to process and transport them from space could revolutionize the global economy. The same is true for energy. Solar power from space-based stations could be harnessed at a much larger scale than what's possible on Earth. With artificial gravity, we could create solar farms in space, where massive arrays of solar panels could collect energy, without the interference of atmospheric conditions or the cycle of day and night. This could provide Earth with virtually unlimited, clean energy, reducing our dependence on fossil fuels and helping mitigate the climate crisis. The real magic of artificial gravity space stations, however, lies in the way they allow humanity to push the boundaries of space exploration. Imagine a spacecraft designed to travel to distant planets and stars. Until now, interstellar travel has been limited by the vast distances between stars, the challenges of propulsion, and the limitations of human biology. With the ability to live in artificial gravity, the limitations of human physiology would no longer be a barrier. Space stations and spacecraft designed for long-term missions could accommodate growing human populations, allowing for communities to live and work in space for generations. In this future, humans could leave the confines of Earth's atmosphere and venture to the stars. The implications are profound. Human civilization would no longer be tied to the Earth. The station we're building today could be the first step toward expanding humanity's reach across the stars. Mars and the Moon could serve as stepping stones, and we could eventually send missions to the outer reaches of the solar system, to the gas giants and their moons, searching for life or even the possibility of colonization. Yet with all this incredible potential, we must also grapple with the consequences. We are building a new reality, one that will test our very understanding of society, ethics, and governance. As we venture further into space, we face questions that go far beyond the technology of space stations or artificial gravity. Who governs these new colonies? What rights do individuals in space have? Should space be open to all, or should it be regulated by international agreements? These are questions that we will need to answer if humanity is to succeed in space, and they will shape the future of our civilization as much as the technologies we develop. Moreover, the impact on Earth itself cannot be ignored. The resources, knowledge, and technologies developed in space will change life on Earth. Space could become a new frontier for international collaboration, fostering peace and cooperation between nations. But there's also the potential for conflict as countries and corporations compete for access to the vast riches and opportunities that space offers. How we choose to approach space exploration and how we manage its wealth will play a crucial role in shaping the future of our world. As we work to construct the first artificial gravity space station, we're not just building a piece of infrastructure. We're laying the groundwork for the next phase of human history, a future where humanity is not just earthbound, but spread across the stars, living and thriving in the vast expanse of space. The road ahead will be filled with challenges, scientific, political, and ethical, but the rewards are beyond imagination. Artificial gravity isn't just about creating a comfortable place to live in space. It's about turning the impossible into the possible and taking humanity's first steps into a new era of exploration and expansion. What do you think? Could humanity truly make the stars our home? Imagine it. The year is 2035. You're standing on the surface of the Moon, looking up at a gleaming structure, an enormous rotating station visible in the dark sky. It's not just a marvel of engineering. It's a beacon of humanity's potential. A place where people live, work, and even sleep under artificial gravity. Beyond it, other space stations orbit Mars, while humanity has spread its reach to distant asteroids, mining them for resources that fuel the next wave of exploration. You look around and realize you're part of something bigger than anything you could have imagined. A new chapter in the story of human civilization, written in the stars. The idea of an artificial gravity space station may have once seemed like science fiction, a dream too big to ever become reality. But we're on the verge of turning that dream into a living, breathing reality. As the first such station begins to take shape, humanity is on the cusp of something extraordinary, not just a stepping stone to space exploration, but the beginning of a new era in which the stars are within our reach. Yet, for all the technological advancements, there's a fundamental question we must answer. What does this mean for us as a species? What kind of society will we build Once we step beyond the confines of Earth and into space, the first artificial gravity space station will be a test, an experiment in not only technology, but also human cooperation, governance, and resilience. We've seen how the International Space Station has become a symbol of international collaboration. Now imagine what it would mean to establish permanent human settlements beyond our planet. The lessons we learn in space will shape the future of life on Earth as well. The technologies, the ethical decisions, and the new perspectives will challenge how we view our place in the universe. Will humanity rise to the occasion? As we strive to master artificial gravity, we also face challenges of unity. The idea of living off-planet is enticing, but it brings complex questions about equality, resources, and sustainability. Will we, as a species, use the resources of space to foster cooperation, or will we repeat the mistakes of history and fight over them? How do we ensure that space remains a place for all of humanity, not just the elite few? The decisions we make today, as we begin to build this artificial gravity station, will echo through the generations that follow. There's another, even deeper question. What happens to humanity itself when we start to live in space? How does the human spirit adapt to such an environment? Our bodies, our minds, and our very identities are grounded in the physical reality of Earth. We know gravity, we know the pull of the Earth beneath our feet. But once we step away from that, once we build a new kind of home that spins in the void, how will we change? Will the experience of living in space change us, physically and mentally? And will it change our relationships with each other, with the Earth, and with the universe itself? We know that artificial gravity is more than a technological leap. It's a paradigm shift, a way of thinking about space, time, and human potential. We are no longer looking at space as an impossible frontier. We're looking at it as a new home. A place where we can push the boundaries of human achievement, a place where we can write the next chapter of human history. But let's not forget the scale of this endeavor. We're talking about building something on a scale humanity has never seen before. The first artificial gravity space station will be a true feat of engineering, a monumental challenge that will require the collective ingenuity and determination of nations, industries, and individuals. It will take time, resources, and energy. But if there's one thing history has shown us, it's that humanity is capable of astonishing feats when we come together with a shared purpose. As we look forward to this incredible future, we must also ask ourselves, what will we do with the opportunities that artificial gravity opens up? Will we continue to push the boundaries of what's possible, or will we become complacent once the first station is built? The future of space exploration depends not just on the technology we develop, but on our ability to adapt, to grow, and to unite in the pursuit of something greater than ourselves. And so, as we stand on the threshold of this new era, let's remember that the construction of the first artificial gravity space station is just the beginning. It's a first step towards something bigger, a future where humanity can not only survive in space but thrive there. It's a future where we will expand our reach to the stars, where we will live, work, and build new worlds beyond the confines of Earth. And most importantly, it's a future where we'll ask ourselves, if we can live in space, what else can we accomplish? What else is possible? The challenges ahead are vast, the unknowns many. But one thing is certain, we've taken the first steps, and the future is no longer something we're waiting for. It's something we're building. Right now.